Okay, try to wrap your head around this. Imagine mapping, well, everything, but all you have are these tiny, kind of blurry snapshots from space, and you don't just need to know where things are, but also exactly how your satellite is moving, how its camera is working, second by second.
Yeah, and you've got, what, a billion stars or
A
objects?
billion things to map, yeah, and 100 billion snapshots to work with. It sounds completely impossible, right?
It really does. And that's basically the scale of the data challenge the Gaia mission faced.
So today, we're doing a deep dive into how they actually pulled it off. We're looking at the computer system behind it all, AGIS, the Astrometric Global Iterative Solution.
Exactly. And AGIS, it wasn't just about the math. It was this incredible piece of software engineering. And understanding how they built it, how they handled all that data, it gives you a whole new appreciation for Gaia's results.
Right? It's like knowing how the sausage is made, but, for groundbreaking astronomy, it really helps trust the final discoveries.
It's a fantastic story of, well, ingenuity meeting this absolutely massive cosmic data problem.
Okay, so let's really try and picture this challenge. A billion unknowns. That's positions, movements for all those stars, plus the spacecraft's own little wobbles, the tiny details of how the instruments work.
All of that. And it's buried in, what was it, 100,000 gigabytes of raw data?
Yeah, 100,000 gigabytes. Trying to find specific answers in that. It's like trying to find one specific email you sent 10 years ago across, like, 1,000 hard drives.
Right. And the genius of AGIS is how it tackles this iteratively. It's not one big calculation. Think of it more like focusing a lens. You keep adjusting, refining until the picture is sharp. They had these four main parts they worked on.
What were those again?
You had the star data itself, the source parameters,
Yeah.
then the satellite's orientation, its attitude, then the instrument calibration, how the detectors were behaving, and finally some sort of global physical parameters.
And they process these in a loop.
Exactly, in a cycle.
Yeah.
Each step feeds into the next, improving the accuracy of all the others, round and round until the whole solution stabilized, until it converged. But here's the thing. The sheer amount of data meant that actually building the software, figuring out how to manage the information flow, that was just as big a challenge as working out the math in the first place.
Which is where William O'Mullane comes in. He saw this coming, right, back in the 90s.
He did. During Gaia's study phase, well before launch, he conceived this whole framework for tackling the calculations using distributed processing. He'd worked on Hipparcos, the precursor mission.
Ah, okay. So he had some experience with this kind of sky mapping data.
Right, but Gaia was just orders of magnitude bigger. His idea was essentially, we can't do this on one machine or even a few. We need a whole network acting together.
And this was the 90s, so that was pretty forward thinking for distributed computing on this scale, wasn't it?
Absolutely. He proposed using Java, which was, pretty new back then,
Yeah.
and really leaning into message passing and networking to coordinate everything. It was a very data-driven concept.
Interesting that they tried an object-oriented database first. What happened there?
Well, it seems the scale or the specific needs just outgrew it, or maybe it wasn't efficient enough. They shifted to more, let's say, traditional database solutions eventually, and they ended up using InterSystems Cache, a high-performance matrix database.
And Gaia actually became like a key use case for that database.
Apparently so. It shows how they had to adapt their tools. And then, crucially, O'Mullane came back to ESA in 2005.
Right, to actually lead the build.
Yeah, to lead the implementation at scale. He put together a team at ESAC, that's the European Space Astronomy Center in Madrid, and they used agile methods, specifically extreme programming, or XP.
Which is all about teamwork, flexibility, short development cycles.
Exactly. Probably essential for tackling a project this complex where you're bound to hit unexpected hurdles.
Okay, let's talk about this data train idea. It sounds intriguing. How did that work?
It's actually a really neat concept for handling the sheer volume. Picture a sort of virtual train continuously running through all the observation data. As it goes, it picks up all the measurements related to one specific star, all its sightings. Then it takes that bundle of data and passes it to the different algorithms that need to process that star's information.
Ah, so it's data-driven. The data for a star triggers the processing steps for that star.
Precisely. It's not like loading everything at once.
Right.
The train brings the relevant data chunk to the processing stations, if you like.
So you're processing object by object or maybe small groups of objects rather than trying to deal with the whole sky simultaneously.
Exactly right. And this architecture was great because it decoupled the complex scientific algorithms from the messy details of how and where the data was stored. The algorithm just gets the object data it needs.
Makes sense. Keeps things cleaner.
Definitely. And this train idea got better over time. Early on, they needed, I think, 4 complete passes through all the data for one main iteration.
4 passes through everything. That sounds slow.
It was, but later they refined it down to a single pass for what they called an outer iteration. Just shows how much they optimize things.
Okay. With, petabytes of data flying around, getting data off the physical hard drives must have been a huge bottleneck. You mentioned minimizing disk access.
Oh, absolutely critical. Disk I/O is always slow compared to processor speed. So they did some clever things to keep vital information in the computer's main memory, the RAM.
Like what?
Well, one big one was the satellite's attitude, its precise orientation in space. They managed to store the entire mission's attitude data, all 5 years of it, in the memory of every single computer node processing the data.
Wow, the whole thing on every machine.
Yeah. Since that attitude information is needed for almost every single calculation involving an observation, having it instantly available in RAM saved just vast amounts of time compared to constantly fetching it from disk.
I bet. What else?
They also kept the results from the previous iteration's calibration calculations in memory, so the improved understanding of how the instruments were behaving was ready to go for the next round. Minimizing disk reads and writes was the name of the game.
So before they actually launched Gaia, they must have wanted to test this whole system, right? With fake data.
Oh, absolutely. There was a major demonstration run at ESAC using simulated Gaia data. This was back around 2012.
How did that go? What kind of computing power did they use for the test?
They used an IBM cluster. It had 14 nodes, 112 CPUs in total, and it cranked out about 0.65 teraflops per second.
So 650 billion calculations a second. Not bad for a test run back then.
Not bad at all. And in that simulation, one full iteration of AGIS took about an hour. They ran 135 iterations continuously.
They were how long?
Nearly 6 days straight. And the total number of calculations was just immense, something like 3 times 10 to the power of 17 floating point operations. That's 300 quadrillion calculations.
Okay, my brain hurts just thinking about that number.
Yeah.
And that was before the real data started flowing.
Right. Based on that, they estimated that processing the expected 100 million primary sources for the real mission would need even more power. Their estimates pointed towards needing something like 5 times 10 to the 19 flops.
Which is way bigger.
Way bigger. Maybe needing around 60 days to run on a hypothetical 10 teraflop machine, which was significantly faster than their test cluster. It just puts the computational scale into perspective.
It really does. Can we see this iterative process actually working in the results? Like how the numbers got better?
Yes, definitely. There are plots showing how key parameters converge. One example is the ppn parameter gamma -1. It's a value related to general relativity.
Testing Einstein, basically.
Sort of, yeah, testing gravity in the solar system. The plots show it starting from some initial guess, and then over the iterations, maybe around iteration 80 or so, it settles down to a stable, precise value. You can literally watch the solution finding the right answer.
That's cool. And what about something more directly astronomical, like the star distances, the parallaxes?
Yeah, there's a great example from Gaia Data Release 1. It shows the size of the parallax updates, how much the estimated parallax for stars changed from one iteration to the next.
Okay, so you want those updates to get smaller and smaller, right? Meaning the answer is stabilizing.
Exactly. Initially, the corrections were pretty large, maybe around 10 milliarc seconds. Still tiny in absolute terms, but large for Gaia.
Remind me, how small is a micro-arc second again?
Think of seeing a single human hair from maybe 1,000 kilometers away. A milliarc second is 1,000 times bigger than that, but still incredibly small.
Right, got it.
So the initial updates were around 10 milliarc seconds, but by the time they got to iteration 200 or so, the updates had shrunk down to about 1 microarc second or even less. That shows incredible convergence to a very precise solution.
And you could see the effect of changes they made during the process.
Yeah, the plots sometimes show little jumps or changes in the convergence rate when they introduce improved calibration models during the run. It's like watching science refinement happen iteration by iteration.
Okay, let's jump ahead to early data release 3, EDR3. That was a major release. What kind of hardware were they running on by then?
Things had definitely scaled up. For the EDR3 solution, they were using 32 computing nodes. Each one had 64 gigs of RAM and 24 processor cores. Pretty beefy machines.
And the total computing power?
The theoretical peak was around 30 teraflops per second. So a big jump from that initial 0.65 teraflop test system.
And storage. Must have needed a lot of disk space.
Oh, yeah. Around 55 terabytes allocated just for the primary star data, though they used about 40 terabytes of that, and another 20 terabytes for the secondary, fainter stars. Huge amounts.
But even before AGIS could start iterating, you mentioned some pre-processing.
That's right, there's an AGIS preprocessor step. Its job is basically to take the raw satellite data stream and sort it very carefully. It actually reads and writes the entire dataset 3 times just to get it organized optimally for the main AGIS runs.
3 full reads and writes. How long did that take?
About a week, just for the sorting and organizing. Then it groups the data into manageable chunks, typically like 1,000 primary sources and maybe 10,000 secondary sources per chunk, ready to feed into that data tree.
A week of prep before the real analysis even starts.
Oh,
Wow.
yeah.
Okay, so for EDR3, how many iterations did they run?
For the final EDR3 solution, they executed a total of 181 iterations.
And how long did each main iteration take on that faster hardware?
For the roughly 14 million primary sources in EDR3, each outer iteration initially took about 90 minutes. They managed to speed that up later for the next data release, DR3, getting it down to about 60 minutes, even with more primary stars included.
Still, 181 iterations at 90 or 60 minutes each. That's a lot of computing time.
It is, and that doesn't even count the setup and testing. They mentioned running something like 200 preliminary test runs just to fine-tune the calibration models before they even started the final operational run for EDR3.
Incredible dedication to getting it right. So let's talk numbers for the final EDR3 solutions. What scale are we talking about?
Okay, for the primary star solution in EDR3, they processed about 6.5 billion individual measurements from the CCD detectors.
Billion, with a B.
With a B,
Yeah.
for 14.3 million primary sources. And from that, they determined about 71.5 million parameters describing those sources: position, motion, parallax, etc.
Plus the instrument and satellite parameters.
Right. Add in about 10.7 million attitude parameters, 1.1 million calibration parameters, and 2 million global parameters. A huge system of equations.
And how many observations per unknown parameter, roughly?
The redundancy factor was about 76. So on average, each parameter they solved for was constrained by 76 different measurements. That gives you a lot of confidence in the results.
That's very robust. What about all the fainter secondary stars?
That was even bigger in terms of raw numbers processed. Nearly 78 billion field of view transits, basically, sightings of stars. This led to converged AGIS solutions for almost 2.5 billion sources.
2.5 billion stars with solution.
Yeah, though it was a mix. Some had the full 5-parameter solution: position, proper motion, parallax. Some had 6 parameters if they could model the orbit or variability, and many fainter ones only got a 2-parameter solution, just position.
And they filtered these results.
Oh, yes. They applied really strict quality checks and acceptance criteria afterwards. So not all 2.5 billion potential solutions made it into the final published catalog, ensuring the high quality Gaia is known for.
It really is staggering. But listening to this, it sounds like it wasn't always smooth sailing. You mentioned it could have easily failed.
That's a really important part of the story, often overlooked. Success wasn't inevitable. Way back in 1999, this whole data processing and analysis challenge was actually flagged as a major risk, a top priority.
Okay, so they knew it would be tough.
They did,
Right.
but believe it or not, the initial funding request specifically to tackle this software and data management problem was rejected.
Rejected. Why?
The comment that came back was apparently something like, not a priority, just wait for commercial products to come.
You're kidding. Wait for off-the-shelf software to solve a unique, unprecedented scientific data challenge of this scale.
Exactly. It sounds almost unbelievable now, but that was the initial response. A real near miss for the whole mission, potentially.
So what happened? How did they get back on track?
Well, it apparently took a long and difficult fight to get that decision reversed and get the resources allocated. They tried a couple of other approaches, first an industrial study, a parallel academic study, but those didn't deliver the solution needed.
So bringing O'Mullane back in 2005 was really the turning point.
It seems so. Giving him the direct authority and resources at ESA to build the system with his team at ESA was what finally cracked it. It just highlights how critical tackling these foundational computational problems is. You can't just assume the software will magically appear.
What a story. So summing this up, the big takeaway is that Gaia's amazing map of the galaxy, all those discoveries, they rely just as much on this absolutely massive software and data processing effort, AGIS, as they did on the telescope itself.
Couldn't have said it better. The sheer ingenuity, the persistence, the cleverness behind AGIS dealing with that data tsunami is a huge part of Gaia's success.
And understanding that process, the iterations, the data train, the sheer scale,
Mhm.
it really hammers home why we can trust the Gaia data so much. It wasn't magic. It was incredibly careful, validated computation.
Exactly. It provides that crucial context and confidence.
Which leaves us with a thought, doesn't it? If these kinds of techniques, distributed computing, agile development, handling massive data flows, were so key for Gaia back then, how are these same approaches enabling breakthroughs now in totally different fields? Medicine, climate science, finance. What huge problems are being solved today because the lessons learned from projects like Gaia? Makes you wonder what's next.